Today's video is a complete shift from what we have been doing. This should be a nice, refreshing change of pace. Let me start here with a simple definition of what a graph is. So the simplest way to describe it is a graph consists of edges and vertices. So a simple, very simple diagram looks like this. This is a simple graph. I don't want you to think they all look like this. I'm going to accentuate the corners of this thing, and I'm going to label them. Those are meant to be the vertices. And the edges are the lines connecting the vertices. So our edges the way we label them is this edge on the top, A to B, I call AB, and that's that line on top. BC is that line on the side. CD is this line down low. And then DA or AD, it doesn't matter which way you put them, it means the same thing. AD will be that line. And then we've labeled our vertices. So the dots we'll use for vertices and the lines we'll use for edges. Now let me start to give you the rules of this game, because this is like a game. Some examples of graphs. And these are very simple to begin with. How simple can they be? Well, a simple dot, just a simple vertex, that does count as a graph. You are not permitted to do this as a graph, though. You can't just have an edge. Every edge must have a vertex at the ends of them. So, but that's a graph. You can do weird stuff like this. That's a graph. Label these things. This star shape is a graph. And I'm labeling the dots A, B, C, D, E. Now what about the other places where it crosses here, here, and here? Well, they don't count as vertices unless I say they're vertices. So that is a different picture from the following. Fundamentally different, I mean. So in this case, I have specified more vertices. Notice that these two graphs are not the same. Graphs will be the same if they have the same number of vertices and the same number of edges. And you can see here, they don't have the same number of vertices. Now you're also allowed a certain degree of freedom when you draw your graphs. For most people, if trying to describe a simple physical situation, they may arrive at something like this, a simple square or a rectangle. Most people would go for something like that when they first start something, but the problem may not look like that. Many times you'll try to make a graph that actually physically looks like the physical situation it is trying to represent. So sometimes if A, B, C, and D happen to be houses, then you may want something like this. So you may have vertices like this, houses sitting next to each other, and then maybe a vertex connecting A to D. These are the same. I'll show you what I mean. If you look at our edges, for the left one, we have AB, we have BC, we have CD, and we have DA. Now look over here at our edges. I have AB, BC, CD, and then AD. So I have exactly the same edges as I had before. And not only that, if you look here, A is connected to both B and D. Look at this one. A is connected to both B and D. Look at B. B is connected to A and C. Look, B is connected to A and C. You can do that for all the vertices. So not only do they have the same number of vertices and the same number of edges, the way they're put together is exactly the same. They just look different. We use a symbol like this, or at least I use a symbol like this, to mean that they're essentially equivalent. So we use the phrase like this. Two graphs are equivalent if they have the same number of vertices and edges and are connected in the same fashion. What is that fashion? Well, I hope to have described it to you by the example that I just did. Many times you'll look at graphs and they will look different. Let me show you some graphs that are all the same. So what I'm going to do is start with what I think would be the rectangle. Let's do that as our first iteration. A, B, C, D. I intend to draw a sequence of graphs that are all equivalent to it, but they all look different. I'm going to use different letters, but not too different, just so we can see how the structure is. That certainly looks different. But then what I can do to compensate, let me call this A with a prime and then B with a prime so that you can follow along the various vertices and how they're related to the graph on the left. That would make this D here. I'll show you how they're the same. Take a look. First of all, we do have 1, 2, 3, 4. I've got 4 edges and 4 vertices in each graph, so that checks. Next, I want to show that they're connected in the same way. So if you look at A is connected to both B and D. Look here, A prime is connected to B prime and D prime. B is connected to A and C. Here, B is connected to A prime and C prime. So I've used the same letters so that you can follow along. Furthermore, this, as we saw in the previous one, is the same as this kind of a graph. You can follow the connections yourself to make sure that they are all the same. So 3 completely different looking graphs. Well, they look good, but they're all the same in the world that we need them in. To give you practice, you'll be required to come up with some graphs and come up with their equivalent looking ones all on your own. So let's do an example of this. Sketch 3 different but equivalent graphs of, so the one I'm going to give you looks like this. I have an A and I have a B, and they're actually connected in multiple ways like this. And then off down here I've got a C. So I want you to invent 3 graphs that look completely different to this thing, but yet they're the same type of graph. So all you got to do is make sure that the letters match up. It's probably a good idea to use the same letters as the ones that are given so that you can follow along. So let's take a look. One of my easiest examples, by the way, the graph itself counts as one of them, but I'm not going to do that. I'm going to draw 3 graphs nonetheless. So we could do something like this. First, just reoriented A and B is always a good idea. And then I can do something like this. I can go, so there's my connections, and then I need one more. And then C needs to be somewhere, so I'm just going to shoot it out here, like so. That's not a lot different looking, but it's somewhat different looking because of this little crossover down here. Then we could do something like this. There's always circular ideas. We could do A, B, and then I could connect them this way. And then somewhere inside of this thing, I could have a C. And then finally, I'm not sure, it's kind of hard to come up with complicated or different looking graphs than that, a lot of different graphs, because it's just not that complicated of a graph. So let's start with A, C, B, and let's see what we can do with this one. I'm going to put dots with each of them. Now the B and A, I know I need to connect in 3 ways. And then I need to connect C to A directly. I could go like this if I wanted to, I suppose. And there you go. That graph looks nothing like the one we started with. And all of these are equivalent graphs. Two vertices in a graph are called adjacent if there is an edge connecting them. So as a quick example of this, if I have something like A, B, C, A is adjacent to B, but not C. B is adjacent to both A and C. And of course, C is adjacent only to B. I don't think I need to spend a lot of time I don't think I need to spend a lot of time on the subject, simply because it is fairly obvious what this means. But you got to be careful here. Let me draw you. There is one thing that pops up from time to time, and that's something called a loop. A loop, A is adjacent to itself. And it seems the loop has some special properties we'll have to talk about later. All right, what we have here is a graph of, it looks like 1, 2, 3, 7 people, and various people are acquainted with each other. So what we want to do is to draw a graph that represents whether people know each other by an edge, and the people would be represented by vertices. Now, this is a good example because it's robust enough to show how everything works. I'm going to use just the first letter of each name because Mike was kind enough to make sure that everybody had different letters for their first names. Now, when you're setting up one of these things, probably the easiest thing to do first is to make it in a circular fashion. So if I started with Nicole here, and I'll just go around clockwise, then Sabrina, Valentina, Graziano, Mike, that Brian does refer to me, and finally Christine. So we're going to go and start with Nicole and see all the people that she's acquainted with. So first, I'm going to follow along here. Nicole is married to Sabrina. I'm going to mark it off here and I'll make a connection there. They don't have to be straight lines, but it's probably easiest to start that way. Valentina is a friend, so Nicole to Valentina, I will make that connection. Mark it off. Graziano is a friend of Nicole's also, so I will make a mark here. Mark him off. And then Mike is family, so he knows her. And there we go. Mark it off. Now I'm going to go to Sabrina. Now Sabrina and Nicole, I've already taken care of the first time. I don't know that I have Sabrina and Mike, so let me see. I do not have Sabrina and Mike. So I could cross over or go around, whatever it is you want to do. I'm just going to do that. Mark it off. Now Valentina and Nicole have a connection, which we've already taken care of. In fact, with Nicole, you can go down and just mark all these off because they have been taken care of. But then I'll forget where I'm at. Next, I'm still at Valentina. Valentina and Graziano, married. Mark it off. And then Valentina and Mike know each other, so I will put a mark, an edge there. Next, I'm moving on to Graziano. Graziano is married to Valentina, which we had before. In fact, with Valentina, I could just cross these off. I didn't even think of that. Once you take care of each of them, like Sabrina, I could take care of their whole column. Now, I don't think I have Graziano and Mike yet, so I will connect them. Oops, I got ahead of myself. Now, Mike and Graziano, well, I just took off what I needed. And Mike and Brian were colleagues. And then Mike is also a colleague of Kristen's. And I've taken care of all of the Mikes. I've not taken care of myself yet. The only thing I don't have is I have not connected me to Christine. And there it is. And I took care of myself there. So the whole thing is marked off, and that will be my graph. So that's one way of drawing it. You could do, really, you can use your imagination to make the picture look any way you want. The only problem with it is the more complicated you make the picture, the harder it is to work with it. The degree of a vertex is the number of edges emanating from it. So in the last example, let me go ahead and do that one. All right, I brought up the previous example. Let's get the degree of each of these, and I'll introduce the notation while I'm at it. So the degree of Nicole equals, let's see how many edges are coming out of that vertex. I've got 1, 2, 3, 4. Now let me go on to the degree of Sabrina. S just had 2 edges coming off of it, so that's a 2. The degree of V equals, for V I have 1, 2, 3 edges coming out of it. The degree of G, 1, 2, 3, also has 3 edges coming off of it. The degree of M, there I think M had the biggest degree, 1, 2, 3, 4, 5, 6. Finally, the degree of B is just 2, as it is with K. This is perfectly fine for these kind of graphs, but there's a couple of situations for which they've had to come up with exceptions or some sort of a specialty. What exactly is the degree of, let me call it Z, this thing? Oh, I drew my loop wrong. What exactly is the degree of Z? Some might say 1, but really you have to think of the vertices or the edges that are coming out of it. And if I were to say cut this here and here, I would have z and I would only have this. If that's all you saw, you would guess that the degree of z is 2. And in fact, that is what it's defined to be. So a loop is a specialized thing. You need to probably, I don't know if you can make it work the way I just showed you and use some sort of a technique like this to make your decision. If not, I suggest just memorizing those things. So while I'm over here, let's connect this. I now changed the degree of z to 3. Let's make this a w. The degree of w will equal 1. Let's call this one over here y. The degree of y equals 0, so that can happen as well. A vertex has even degree if its degree is an even number. This almost sounds too silly to write down, but we need to define it. My guess is you could do this one on yourself as far as define it. A vertex has odd degree if its degree is an odd number. Draw a graph with 4 vertices, but where 2 vertices have even degree and the other 2 vertices have odd degree. Try to make these as simple as you possibly can if you're asked to do this. That's my advice anyways. So I'm going to have 4 vertices. As I usually do, I'm going to try to rearrange them in something of a circular or square fashion like this. And I'll start simply this way. Now I need 2 of them to have even degree. So I can do, like from A, I can do something like this and this. So A has an even degree of 2. Both B and D have odd degree of 1. And C has even degree of 0. So this will work. I'll put a check mark there. Degree of A is 2. Degree of C equals 0. 0 is an even number, by the way. The degree of B is the same as the degree of D, and they're all equal to the odd number 1. If you wanted to, you could also do this. I noticed that I can take and connect B to C, for example, and then C would become an odd vertex, but then B would become an even vertex. The total degree of the graph is, all you do is add up the degrees of each of the vertices, really. 2 plus 0 plus 1 plus 1. That is in order A, C, B, and D. So this adds up to a total degree of 4. The total degree is the sum of all the degrees of all vertices in the graph. All right, what we have here is a picture of various states. You got Michigan. Let me write down which ones are which. I may not have thought out this example very well because it's very dark. So let me see if I can find ink that I can write on that will show up. Very good. My M shows up very nicely. All right, Illinois. So, and Indiana. Well, both of those start with I. So I'm going to do I-L for Illinois. And then Indiana, I will just use an I. Then, of course, we have Ohio, Pennsylvania, West Virginia, and Kentucky. Now, your job is to make up a graph that has an edge if the states share any amount of border, not corners. Like, I don't know if I have an example here, but it looks like everybody sort of shares some state with somebody else. Nobody is off to a corner, so I don't have to worry about that. Now let me go and grab my regular ink and draw a picture almost identical to what I see here. There'll be my M, and then I'll try to even do it in order because I think that's going to be the easiest thing. W is down over here. K is down over here. And then next to Ohio, we have Indiana. And then we have I-L. And I already have the Michigan. So let me go ahead and put dots for all of these things. Now let's go ahead and make our connections. Let me start with Michigan. If you take a look, Michigan does share some border with Illinois. So I'm going to make a connection there. It also shares border with Indiana and Ohio, so I'm going to make connections there. I don't see Minnesota or Michigan connected to any other states in this region, so I think I'm done with it. Now I'm going to move on to Pennsylvania. What is Pennsylvania connected to? It's connected to both Ohio and West Virginia. Now, as you use them, if you want, you could probably put a mark through them just to let yourself know that you've already handled them. Although I see they're impervious to my marks. Let me go on to the next one. W is connected to Pennsylvania, Ohio, and Kentucky. So I've already taken care of West Virginia to Pennsylvania. I have not taken care of West Virginia, Ohio. I got that. And now West Virginia to Kentucky. And now I might as well move on to Ohio. Ohio is connected to Pennsylvania, which I did. Ohio is connected to West Virginia, which I did. Ohio is connected to Kentucky, which I have not done yet. And Ohio is also connected to Michigan, which we have handled. But Ohio is also connected to Indiana. Now let me move on. I don't think I've handled Kentucky yet. Kentucky, I've got it connected to West Virginia and Ohio already, but it is also connected to Indiana. And look down here. It looks to me like Kentucky and Illinois share some border. So if that's true, then I'm going to connect Kentucky and Illinois. So I think I've handled Kentucky. Now let's move on to Indiana. Indiana, I've already done Michigan, Ohio. I've done everything around it except for Illinois. So let me go and sneak it there without going and touching my letters. And I think that is the only connection that I had to make yet. And then finally for Illinois, by the time you get to Illinois, everything that's connected to it has already been spoken for. So this is how you can make a graph out of a physical situation. These kinds of graphs are very important because at one time, places like Ohio and Michigan were centers for a lot of business. A lot of boats went up and down these Great Lakes and benefited the businesses that were all along those waterways.